Thank you, everybody, for being here, attending this session. So it's my pleasure today to start speaking on design of lattice structure and metamaterials in general. Today, we're going to focus on the influence, again, of the process. So I would like to thank the plenary speaker of today for introducing the importance of the additive manufacturing process itself inside the parameters of the fatigue in this case. And we are going to check one of the most influential parameter, which is the building orientation. And also, we're going to double check the influence of the stress ratio in the fatigue behavior for miniaturized specimen. Okay, so we want to talk about design. We want to talk about fatigue. So we need to understand what is fatigue and what is driving fatigue. So we can identify different factors for this. First one is, of course, the material. So as we have seen before, different materials has different defectosity and also different, of course, qualities. We will speak today about 316L, which is a stainless steel, very common for different kind of application in additive manufacturing. Then we have, of course, the geometry. This is a very important topic because the topology of the lattice structures really drives the concentration of stresses. And this can be true when we consider, let's say, a geometrical feature like truss and nodes in this case. But this is also true for the geometrics, for the geometrical detail of manufacturing-induced defects. So, for instance, here we have failure, and this may be caused due to a very specific and local geometry that we have. This is true for both internal porosity, but also for surface defectosity, such as partially melted particles, for instance. We started this journey some years ago, in particular with the works of Dr. Murchio, with miniaturized specimen. So the idea is testing lattice and building lattices and understanding lattices. It is quite challenging because they are complex structures. So the idea is to break down this very complex structure and try to do analysis on more simpler components, which are the building blocks of the lattice geometries. So that's what we call miniaturized specimens. We have done this, and for this specific study, we worked on 3 different building orientation for the same geometry with this very precise LPBF concept laser machine. So we started this, but this comes also from a long history, as I mentioned you before, and we worked a lot on titanium, where we look at, again, the influence of printing orientation, and we found the relation with the fatigue behavior of these components. So as you may see, for titanium, there is a large variation in terms of fatigue response based on the different load case scenario and also for the different printing orientation. This is very important, and we are going to compare this result with the one that we obtained on stainless steel now. We followed a workflow which starts from, of course, the manufacturing, so the design and the printing of these components. But, of course, it is very important to understand what is the as-built geometry of this miniaturized specimen, and so defects. Therefore, we perform, firstly, a methodological characterization based on very fast and computational, and cost-effective stereo-optical images. So we took 2 images, one for each side of each specimen, in order to understand through image analysis what is the real dimension of our component. So we hypothesize the cross-section as elliptical, and we try to compute the cross-section in both as average dimension and both for image minimum dimension. So starting from this background, we can identify already some pattern in our printing. So firstly, we can see that for 90-degree specimen, we have a clear reduction with respect to the nominal diameter, both if we consider average and minimum cross-section. This is, of course, a manufacturing use effect, which we were not expecting. On top of that, we have both for 45 and 30 degree specimen, we have an increment in the nominal in the S-build diameter with respect to the nominal one. And this is something that we understand in a better way, because of course we have the staircase effect, where the different layers are printed on the powder and not on the solid material. And therefore, we can have more inclusion of surface defectosity, such as partially melted particles, or drosses, and so on and so forth. So we can understand, firstly, this relation here. But this is not it, of course. Once we are happy with the characterization, with the methodological characterization, we started with quasi-static tests. So static tests, basically. We, of course, tested all of the 3 printing orientation. This is just some of the results. We tested 3 specimens of them. I just took some of them. And what we observe here, and this is something which is extremely interesting, and if there are people interested in that, I think we can talk about it later in detail. As you may notice, we have that for 90 degrees specimen, we have a resistance which is quite outstanding with respect to the other 2 directions. Well, this is not normal, and we should not expect that, because basically the specimens are exactly the same. The only thing that is really changing here is the cross-section. So a clear definition of what a cross-section is extremely important, because for 90 degree, we have a cross-section which is almost half of the nominal one, meaning that the ratio between the surface defectosity and the actual cross-section is very important, and therefore the load-bearing cross-section is a fraction of what we see, and we cannot compute it properly. So this is an open question. I just want to show you this result in order to start a conversation on the topic. We went on with the fatigue testing. So as you may notice, we use a very specific setup, and we select 3 different load casing scenario, from complete tensile to fully reversed to mainly compressive load case, in order to assess the effect of the mean stress. What we obtain are these curves. So as you may notice from the different colors, there is not much difference in the response on the fatigue response for the different printing orientation. Meaning that for the selected setup, so for the selective manufacturing setup, is guaranteeing a quite, how can I say, homogeneous response across all the printing orientation, meaning a high printing quality. What we observe instead, for instance, printing and a high diagram, is that we have an effect, of course, for all of the different orientation based on the load case. And this is clear, of course, but something that, and this is clear and something that we expect, because if we move from compressive regime toward tensile regime, we have a decrement in the fatigue properties. But something very, very peculiar that we found is that we have sort of a threshold in between R-1 and R0.1. So in between fully reversed and tensile ones. So what we expect here is this point to fall down, but this is not happening. And why is that? We suppose that there is a very strong influence of the material, which is able to accommodate local plasticity in order to generate a more blunt crack tip, and therefore a reduction of the fatigue, let's say, damage. We went on analyzing the porosity of our components, and what we noticed from this microstructural analysis, this metalographic inspection, we found that there are some pores which are very close to this from the surface. And these are quite important because we found out that these are, in most of the cases, the location of the crack nucleation. So the nucleation starts from subsurface pore and then grows, the crack grows till the complete failure of the component. So I would like to head toward the conclusion. So what we understood from a design point of view is that with this material, with this specific printing setup, Well, there is not much difference given by the printing orientation, which is a good pro because you can print your component in whatever direction you like. But at the same time, of course, we need to take into account what is the mean stress effect, even if with this specific material, we have an influence of the local plasticity able to limit the criticality of tensile behavior. And then in terms of fractographic surface, we have that the cracks nucleates from a subsurface pore and then grows till the complete failure of the component. What we plan to do, starting from here, is to study the impact of the plasticity on this material through very specific finite element models, which is basically the only tool that we have in order to understand what is really going on inside this miniaturized specimen. I would like to acknowledge the founding that made this possible, which is the Butterfly project from Professor Berto. And I would like to thank you for your attention, and I'm very happy to answer your question. Thank you very much.
So is there any question from the audience? I think we can answer. I don't know how it works exactly.
Okay. Okay. Thank you for the presentation. I have two questions, if it's possible. Probably I don't understand, and will be more clarified. First, this cross-section is built as a border, full fill material, and inside is only lattice?
So these are basically cylindrical specimen.
Cylindrical, okay. Have border as an outside surface is fully filled, and inside only inside the direct cross-section only inside is the lattice. On the border is full material.
Yes.
Okay.
Basically,
okay, this is important.
We are actually printing a cylinder.
Okay, and inside
with
the
usual
lattice.
techniques
Okay,
of LPBF. Okay. So basically, you have a contour layer first, and then
this
you have the edge.
Okay, this is my question. Okay, and second one is how you calculate the cross-section for the amplitude of stress when you compare, for example, static tensile curve or other, because if the cross-section is the same and you have different orientation of building, you compare different intensity of force to the point.
Okay, let me start answering the question from the first part. So what we use for computing, sorry, too fast. For computing the stresses here, we use the minimum cross-section that we identify in the optical measurement that we found here. So basically, we identify the profile of our component, and then we took the distances from this yellow line to the green line that we have here, and we took two images. So one is the horizontal one that you see there, and then the other one is the vertical one. We collimate the two and do the hypothesis that we are actually looking to an ellipse from two sides. And we can build again the ellipse, basically taking the measurement of the two main axes. Of course, this is a simplification. This is not like having a CT version of a CT complete 3D reconstruction, but this is very cheap and very fast. We can do it in
the same approach for all these three directions of building.
Yes, we have done that. Yeah.
You obtain different values of cross-section.
Of course.
This stress is complicated to say it's comparable because you have the force over the different cross-section that you calculate different intensity of force as a definition of stress here. If it's correct, this comparison, these three stresses with this three orientation, because the cross-section is different.
Okay, so let's say that we need to normalize it somehow. And let's say that we are in the hypothesis of having a fully, let's say, how can I say, plane specimen. Of course, this is not true locally. So locally, you for sure have stress intensity intensification. We studied that a bit in detail with more complex model with respect to these. But from a starting point, so starting from a characterization of the material, we have proposed this methodology for now. We can discuss a bit more on this if you like. And please, let's catch up afterward because, yeah, okay, yeah. Because otherwise the chairman need to tell me that we are a bit late now.
I was going to.
Thank you very much.
So thanks again, the speaker.
Okay, so now let's reverse role. And it's my pleasure to introduce Professor Dr. Murchio for the next speech. Next session.
Avanti, avanti.
Okay.
Okay. Okay. Good afternoon, everybody, and thanks to be here to this symposium and also to this presentation, which will be about the corrosion fatigue behavior of laser powder bed fusion Ti64 lattice struts. So similar specimens to the one that Dr. De Biasi showed before, but different material. This work has been done in collaboration in between La Sapienza University of Rome, the University of Trento, and the Northumbria University based in UK. The main topic here is metal additive manufacturing for biomedical applications, and mainly the employ of architected cellular material that we also know as lattice structures as metamaterials for the design of next generation prosthetic devices. Why this? Because this kind of new class of engineering materials allows both a morphological mimicking of the bone tissue and also a tunability of the mechanical properties to properly match or almost match the properties, such as, for instance, the elastic modulus of the bone tissue in the implantation site. When we are dealing with this kind of devices, we are dealing with really complex design. And this design, before going to a market release, needs to follow some regulatory pathways, which encompass different steps, starting from some risk assessment, verification test, which can span from device to material to biological characterization, then process validation, and the regulatory submission processes. In the case of this kind of implants, basically the workflow is the same as the common, let's say, golden standard bulk implants. But the critical and crucial step for AM implants is the process validation, as we have already seen also in the plenary before. And this is critical for AM devices. And indeed, if we look at the AM cleared medical devices that are up to market at the moment, more than 40% of them leads to failure when we are dealing with adverse events of this. So not the 40% of all of them as failure, but when we have adverse events, we have 40% of failure. And this is mainly the major concerns that industries have to employ this kind of metamaterials, in particular structural integrity issues, but specifically also fatigue-related issues, which are mainly for AM materials associated to the process-induced defects. So the enhanced surface roughness, stair-stepping effects, and so on and so forth. For this reason, when we're dealing with AM device, we need to basically account for this kind of as-built enhanced surface roughness, and it's really hard to fully remove and properly remove it. Also because on one side, this is beneficial for osteointegrative processes and for cell adhesion and proliferation, despite on the other side, we already said, it's pretty detrimental for fatigue. But one thing which is often overlooked is the corrosion behavior, since this kind of implant should be designed in order to be implanted in a specific body fluid with corrosive ions and a corrosive environment. And so this is basically the aim of this presentation and of this work, is trying to understand what is the fatigue behavior of Ti64 laser powder bed fusion strut specimens or metamaterials, particularly considering the role that this kind of defects and the enhanced as-built surface roughness has and might impact on the corrosion fatigue behavior. To do so, we decided to print the miniaturized specimens that has been already described. It basically changes the material and changes the printing orientation. The dimensions and the specifications are the same. And we adopted, again, the morphological characterization and based approach on stereoptical images in order to retrieve the average and the minimum cross sections, which will also compare with respect to previous specimens of the same material that we used for other research. And we are in a good line with the other work, just stating that the printability is pretty consistent also if we change the different orientation. Given this, how can we test these miniaturized specimens for corrosion fatigue? We had to build some in-house setups. Usually for air-tested specimens, we employ a Bose electroforce equipped with a 200 Newton load cell. In order to do corrosive tests, we had to add a vessel, a customized vessel that we made in-house, which basically contains a film of liquid, of medium, which only soak the central part of the specimen, avoiding the gripper to be soaked. And then through a connection with peristaltic pumps and piping systems, we are able to create a closed loop of fluid with a constant flow rate and with a constant temperature, which is set at 37 Celsius degrees, considering it as the body temperature. The fluid that we have decided to use is PBS, phosphate buffered saline solution, which particularly in terms of ions that might be critical for corrosion and corrosion fatigue, is pretty comparable to the chemical composition of blood plasma, actually a little bit more critical. The tests were performed at 1 Hertz of frequency with a runout set at 10⁶ cycles. It's a pretty low frequency, but it aims to mimic the walking cyclic gait of a human being, and have been done in a tension-tension fatigue regime at 0.1. It's pretty evident the results and differences that we do have in between air-tested specimens and PBS-tested specimens for the fatigue experimental data, and this is particularly with a 25% drop at 10⁵ to 10⁶ cycles. So it's pretty clear that there is an effect of the environment, and we need to understand how and why this effect happens, and what kind of dynamics might change in between air-tested specimens and PBS-tested specimens. And this has been done by basically investigating the fatigue fracture surfaces. We decided to do a sort of pair analysis, coupling an air-tested specimen with a PBS-tested specimen at the more or less same numbers of cycles, both in the cleaned and in uncleaned version, so 2 different sides of the specimen, one cleaned in order to remove the corrosive products, and one uncleaned to preserve these corrosive products. Probably here is not super easy to see them, but we do have more or less the same type of initiation mechanism, which occurs from notches on the outermost surface, also in combination with lack of fusion or subsurface porosity, which is really close to the surface. Here you might appreciate some striation lines. And this happens both for air-tested and PBS-tested specimens. The main difference is that in here, despite in both cases we do have a transgranular crack which propagates towards the final failure, we do have some crack branching in air-tested specimen, things that instead is not visible in PBS-tested specimen, probably suggesting that there is a lower energy dissipation mechanisms in PBS-tested specimens, suggesting hence a higher fatigue crack growth rate. And then we also can see in the unclean specimens the presence of NaCl salts, which are the darker spots, which are not uniformly, homogeneously deposited in the regions where the crack started and then further propagated. We try to understand if our hypothesis of different energy dissipation mechanisms in between the 2 types of specimens could find something in agreement in literature, and we found actually agreement for a work of Zhao and al., which has been published in 2023, particularly considering that our microstructure is a lamellar microstructure, in which, as you can see from the fatigue crack growth rate tests, we do have severe differences in between a body fluid solution and an air-tested solution, particularly in the Paris regime. So the idea is that probably is in the fatigue propagation that we do have the major changes and effects of the corrosive environments with respect instead to the initiation, which might be the same. However, we wanted to do some step more and investigate also the different chemical ions that we have in the composition on the overall surface of our failed specimens. And what we could see is that we confirmed the presence of NaCl, but we also saw an increased content of oxygen, phosphorus, potassium, and aluminum, which might leads to an idea that also the initiation has been altered with a local breakage of the passive TO2 film and the formation of potential corrosive oxides. On top of this, since we would like to try to find a way to properly design these prosthetic devices for a wider and safer designs against fatigue, we CT scanned some specimens. We identified all the valleys, within the specimens, and we isolated the 10% deepest valleys. We did basically the same with porosity, and we decided to try to see if we could find a way to identify the killer defects that leads to the failure of these components by basically defining a an interacting metric in between the surface defect and the subsurface defect based on Murakami parameter. Basically, this is just a distance metric, which if it's respected, we consider the defect as a single defect. Otherwise, we consider it as two different defects. What we have noticed is that for air-tested specimen and one PBS-tested specimen tested towards the low cycle fatigue, we do have that the combination of the valley, of a deep valley, and of a pore leads to the overall, are the killer defects that leads to the failure. And these are among the top 5%, the top 5 most deep defects. However, when we are going towards what we call, let's say, medium to high cycle fatigues within our SN fatigue regime, we do have instead that just a valley which is in between the 40% of the most critical valleys, so not a really deep valley, leads to the failure. This probably suggests again that there might be a change of mechanisms due to the fatigue, the effect of the corrosive environment on the fatigue initiation. And with this, I just would like to conclude, just wrapping up. We can see a decrease of about 25% at 10 power 5 to 10 power 6 cycles for the fatigue tested specimens, mainly associated, in my opinion, to the crack propagation part rather than the crack initiation. We also tried to, despite preliminary, develop some micro-CT-based approach for the fatigue assessment of these killer defects. And with this, I would like to thank you for listening, and I would like to thank you, ERC and the Royal Society that allowed us to do this kind of experimental research. Thank you very much.